Hi, I'm Mr. Franklin, and today we're going to introduce the topic of gravity, weight, and mass. And just keep in mind we are going to stick to some very basics here. I'm going to show you some more complicated stuff by way of explanation, but in the end, I want you to, we're going to wind up keeping it simple when we get to the math part of it. So, starting off, gravity. Sir Isaac Newton basically defined gravity as the attractive force between any objects with mass. Now, what I want you to point out here is what he really said is that we know how much that force is. He told us what the quantity of force between those two would be. He never really explained what gravity is. And we never really had a good explanation. Now, Einstein has come along, and he has basically, with his theory of general relativity, stated that space and time are made of a single fabric that is distorted by objects with mass. And when these objects with mass encounter these distortions of other objects with mass, the result is the force we call gravity. Now, that's simplified because there's a thing called the Higgs field. There's all kinds of stuff that plays into this, but that's a very simple explanation. So what Einstein said was space is made out of a single fabric. So if this is a sheet of paper, okay, and it is flat, okay, if I take my sheet of paper and I put something on here, let's say we put if this is space and time, let's say we put the sun in here. The sun's mass is going to warp our fabric, okay? It's going to warp the fabric of space and time and basically, in a sense, create a hole or a little dip in space. So if something is traveling along, it will slide down into the hole and then it might get captured. So the Earth is orbiting because it's captured in what we call a gravity well. I'll try to put some videos on that so you can get a better view of what that actually looks like. Okay, so this is what Newton actually said. Force due to gravity equals big G, which is the gravitational constant, times m1 times m2 divided by r squared. So we have the mass of one object times the mass of a different object divided by the distance between the objects squared. Now we use the letter r instead of d because generally this includes the radius to the center of the object. So if you look at your equation sheet, so you got your equation sheet, okay? We're in the force column here. We're going to be here in the force column, okay? So if we take a look and we go down, we have our force due to gravity, okay? Fg equals G times m1, m2 divided by r squared. The gravitational constant is big G, and big G is right here. So we have our acceleration due to gravity, which we've already talked about, and now we have this guy. Now, we're not going to go into the math that you would do with scientific notation in this course, 6.67 times 10 to the negative 11th. But anytime you have an exponent with a negative value, that's the same as if we were dividing. Okay, so this number is actually the same as 6.67 divided by 10 to the 11th power, which means this is a really, really tiny decimal. Okay, it is, 10 zeros in front of a 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7. Really, really tiny number. Okay? But this can be used to find the force of gravity between any object with mass. Okay? So if I were to take a 1 kilogram bowling ball and place it on the Earth's surface, I would take the gravitational constant, 6.67 times 10 to the negative 11th, times the mass of the bowling ball, times the mass of the Earth, which is 5.97 times 10 to the 24th, and then I would divide it by the radius from the center of mass of the Earth to its surface. Now you got to understand that to get a more accurate value, you would actually have to do some calculus to account for how far each little piece of mass of the Earth is, but in general it works out to be pretty much the same number. If I plug in these numbers and I do all the math, what you're going to wind up with is a number that winds up being close to 9.8 newtons. And for those of you math wizards out there, 6 times 6 is 36. 6 squared is 36. So, and this is almost 10, by the way. So we're going to have something that's equal to 1, and then it's a matter of how many zeros all our exponents equal to. So negative 11 and 24 is going to be 13. And then we're going to have 1, 2, 3, 4, 5, 6 decimal places squared, which is 12. 13 divided by 12 is going to be times 10 to the 1 power. So we're going to have 1 times 10 to the 1, which is basically 10. Okay? And that's all using exponent rules for math. The good news is in this course is I'm not going to make you do that calculation. Okay? So in this class, what I'm going to want you to do is do an approximation. You're going to get a question that says, if I have two objects that are 1 meter apart, and I take the mass of one and the mass of the other one, if I take and double that mass, what is the force due to gravity going to become? Okay? So to keep it really simple, we're going to make up numbers. So we're going to pretend like big G is 1. The mass of the first object is 1. Mass of the second object is 1. And the distance between them is 1. So our force is going to be multiplied times a factor of 1. So when I double the mass, this is what's going to happen. Big G is 1. The mass of the first object has been doubled. The mass of the first object or second object stays the same, and the distance stays the same. So 1 times 2 times 1 is 2. Divided by 1 squared is 1. So 2 divided by 1 is 2. So I'm going to double the force. So if I double the mass, I'm going to double the force. So if I triple the mass, guess what happens? So the force is going to triple. Okay, what if I double both masses? Then it's going to be 1 times 2 times 2 divided by 1 squared equals, I'm going to get quadruple. I'm going to multiply the force times a factor of 4. So this isn't actually going to give you the actual value for the force, but it can tell you how the force is going to change and by how much. Now, the question on your test might actually ask a more difficult question, which is, what happens if I change the distance between the objects? So let's say we start with a distance of 1 meter. So 1 times 1 times 1 divided by a distance between them of 1 meter is equal to the force that we started with. If I double the distance, I take these objects and so they started at 1 meter, and now I'm going to double that distance. So I'm going to move this one and this one, and I'm going to move them further apart. Okay, so I'm doubling the distance. Okay, what's going to happen? 1 times 1 times 1 divided by 2 squared. You got to be careful of that squared. So that's going to be 1. What's 2 squared? 4. So if I double the distance, the force between them is going to drop by a quarter, by a fourth. If I triple the distance, it's going to drop by, be careful, what's 3 squared? 9. So it's going to be dropped by a ninth. Okay, what if I bring the objects closer together? So I start here, and now I'm going to go from whatever distance I start at. So let's say 1 meter. And now I'm going to cut the distance in half. What happens now? So we look at our equation, 1 times 1 times 1 divided by, I cut the distance by a half, but you got to square it. So I get 1 divided by 1/4, because a half squared is equal to a fourth. What in the world do I do with that? So when we divide by a fraction, we multiply times the reciprocal. So what's the reciprocal of 1 divided by 4 of 1/4? The reciprocal is 4. So I'm going to multiply 1 times 4, and our answer is going to be 4 times the force. So if I bring the objects closer together, I'm going to make the force get larger. So if I cut the distance in half, it's going to increase by a factor of 4. Okay, what if I cut the distance by a fourth? Not a half, but a fourth. We're going to square that, and I'm going to get, so we're doing our 1 times 1 times 1. So I'm going to get 1 over 1/16, so the force is going to increase by a factor of 16. Okay? Promise you, just remember that this is not the actual force. It is a factor that we're going to multiply the force times. But if you do that, you don't have to do that kind of math, okay, for our test. Okay. So we've talked about Newton's second law, and we said that Newton's second law is the, as Newton actually said, is the time rate of change of momentum. So momentum is mass times velocity. So delta is the change. So change in momentum times mass times velocity divided by change in time. Now, with the bowling ball, the mass doesn't change as I roll it down a hill. So the mass is constant. And then we have delta V over delta T, which we've learned in our kinematics that that's just acceleration. So F equals mass times acceleration. Now, how does this work with gravity? Well, force due to gravity is also equal to mass times little g.
I need to run the restroom. So
Okay.
Can you just kind of keep an ear out?
Yeah, sure.
They're fine, but just want to have an adult know that they're there.
Sure.
I'll be right back.
Okay, all right.
Thanks.
Okay, so we can also calculate the force due to gravity in this way, where we have mass times acceleration, but the acceleration is the acceleration due to gravity. So earlier, we did this whole big equation, and we got 9.8 newtons. Well, what is that? It's 1 kilogram times the acceleration due to Earth's gravity, which is 9.8. 1 times 9.8 equals 9.8. Okay? And that is the weight of the bowling ball. So force is a weight, or weight is a force determined by the mass of the object. If I go to the moon, and the acceleration due to the moon's on the moon's surface is 1.6 meters per second squared. What's the weight on the moon? 1.6 newtons. Did the mass change? No. Did the force change? Did the weight change? Yes.